Lecture 4.2 Top-down Techniques for Synthesis of Nanomaterials. Let's discuss some of the important top-down synthesis methods of nanomaterials. Top-down approaches start with bulk materials and breaks them down into nanoscale structures. First, mechanical milling method. It is high-energy ball milling technique in which steel or carbide balls are used to break down bulk materials into nanocrystalline powder through repeated impact and accretion. In this process, coarse powders are placed in a sealed, often inert atmosphere container with milling media and rotated at high speeds for several hours, causing repeated fracturing and cold welding of particles. The limitation of mechanical milling method is that the materials obtained by this method has broad size distribution and structural defects. And the major advantage of this method is that it is a cost-effective, scalable method suitable for large-scale production of metallic, ceramic nanoparticles, nanocomposites, and alloy with enhanced properties. Second in this line are lithography techniques. Lithography techniques for nanomaterial synthesis are primarily top-down, high-precision methods used to create patterned nanostructures and hybrid nanoparticles on substrate. These methods allow for precise control over the shape and size of one-dimensional, two-dimensional, and three-dimensional nanostructures, crucial for electronics and research applications. Key lithography techniques include photolithography, electron beam lithography, and nano imprint lithography. Lithography techniques are highly precise but expensive. Like photolithography or electron beam lithography are widely used in semiconductor fabrication. For example, in fabrication of nanochips in companies like Intel. Third is etching technique. Etching techniques are crucial top-down approaches for synthesizing nanomaterials by selectively removing atoms to create precise, high surface area structures like nanotubes, nanocages, and porous materials. These methods enable tailored morphology such as hollow nanostructures for applications in catalysis, energy storage, and semiconductor devices. It is widely used in nanotechnology and semiconductor manufacturing. Etching is a process for transferring a pattern into a material. It is accomplished by using a variety of different techniques. The two most common techniques for etching a pattern into a material are wet etching, which uses liquid chemical solutions, and dry etching uses plasma or reactive gases. Etching technique has many advantages. First, it allows high precision. It can create very fine nanoscale patterns. Second, it makes controlled fabrication possible. The depth and shape can be accurately controlled in this process. 3. It is suitable for micro and nano devices, which are essential for semiconductor and MEMS fabrication. Fourth, it provides good surface patterning. It enables complex nanostructure formation. And fifth, it is scalable for industry, essentially dry etching in semiconductor manufacturing. The limitations of etching techniques include, first, high cost, as dry or plasma etching equipments are very expensive. Second, surface damage. Plasma etching may damage delicate nanostructures. Third, chemical hazards. Wet etching involves corrosive chemicals. Etching technique has limited material selectivity. Some materials are difficult to etch selectively. Then process complexity. It requires controlled environment and special expertise. In conclusion, we can say that top-down nanomaterial synthesis techniques provide a controlled and reliable approach for fabricating nanostructures by breaking down bulk material into nanoscale dimensions. Methods such as lithography, etching, and mechanical milling have played a crucial role in advancing modern electronics, MEMS, and nano devices. Although these techniques offer high precision and industrial scalability, they may involve high cost, material wastage, and structural defects. Therefore, while top-down approaches remain essential in nanotechnology, selecting the appropriate method depends on the required applications, cost, and desired material properties. And understanding these techniques helps us appreciate how nanoscale engineering transforms bulk materials into functional nanostructures that power today's advanced technologies. And to dive into the amazing world of nanotechnology, catch me on my YouTube channel, PHYSIFER. Thank you. We'll be back with next. Thank you. We'll be back with next lecture soon.